Good morning, everyone, and welcome to EDP and Applied Mathematics Seminar. It's a pleasure for me to open session 91 of this seminar. Today we have two excellent speakers, Gustavo Ponce and Aurea Martinez Varela. Introducing to Professor Gustavo Ponce, we have to Professor Roberto Capistrano. Thank you, Roberto. You can start.
Oh, thank you, Juan. Thank you, Professor Gustavo. Hi, everyone. Good afternoon. Well, it's a pleasure for our seminar to welcome Professor Gustavo from University of California, Santa Barbara. Before Professor start, let me give some words about the career of Professor Ponce. Professor Ponce was graduated from the Central University of Venezuela in '76. Okay, after that, he moved to US and started his graduate, the master and PhD in the Wuhan University. Moreover, Professor Ponce has a visiting lecturer at the University of California, 82 to 84. After that, as assistant professor in Central University of Venezuela, 84, 86. And after University of Chicago, Pennsylvania State. Finally, he's right now full professor at University of California. He was also visiting for many academic institutions like University of Bonn, Paris-Sud, Henri Poincaré Institute, Autonomous University of Madrid, IMPA, University of Basque Country, among others, okay? Professor Ponce is interested in mathematicals with application in physics, harmonic analysis, and nonlinear PDEs. He also was invited as a speaker at the ICM in 2012, okay? Today, Professor Ponce will give us this great opportunity to attend his lecture, Special Property of Nonlocal Nonlinear Dispersive Model. Thank you, Professor, for this nice opportunity.
Well, thank you for the introduction, and I would like to thank all the organizer for this kind invitation and the opportunity to talk about some recent results and not so recent too, and some work in progress. As the title says, we will be talking about some kind of a special property of non-local nonlinear dispersive model, and most of the time we will be talking about unique continuation. And the problem that we have in mind is the following. We have to study local unique continuation, and for local unique continuation is more or less is to solve the following question. Suppose that we have two solutions that agree in an open set. Can we prove that they agree in the whole domain of definition? That is the question, very general question. Most of the time, we will be talking about the initial value problem, but not restricted to this. Well, sometimes, as we will see, this is too strong to be proved. You can only prove this with some restriction. For example, you have to assume that one of the solution is a particular one. You cannot take any two solutions that you wish. One of the solutions, maybe you have to say that it's 0 or is a constant. We will see that in some of the examples. Of course, if we have this question, we have to eliminate all the models that have finite speed of propagation, because, I mean, if you have finite speed of propagation, you start with compact support, you will stay with compact support, you will be 0 in an open set, and you are not 0. That's clear. That means that we have to remove hyperbolic equation, and we have to remove other model. For example, we have to remove the compact tone equation that is something that look like the KDV, but it have here a square. Then it's a kind of a degenerated KDV, and have solutions that are compact, have traveling wave solution that have compact support, right? And the solution, of course, is not too smooth. You have to understand the solution in the weak sense and so forth. Also, another problem that we have to remove is that if we consider the porous medium equation, because if you can have solutions that have compact support for a long period of time. right? Then our first example is this one, and this will be the model that we would like to see. It will be the KdV, the typical KdV equation, right? And we are considering this in the space, in the full line. Then in 1987, Giancloso and Bruno Scherer proved that if you have two solutions, very general solution of the KdV equation, and they agree in an open set of R in an interval of time, they are equal everywhere. This is the kind of result that we would like to have, right? And the proof doesn't need the KdV. It can be any power. I mean that it applies to nonlinearity of this form. Okay, it can be 1, 2, 3. It can be any. And the proof is based on Kahneman estimate. And right, there are some results for the Schrödinger equation due to Viktor Isakov, but we will stick with this result from Jean-Claude and George. Okay, what can you say? What more can you say for the KdV? Well, Chant proved the following. If you have a solution of the KdV equation that vanishes in two semi-lines, it vanishes here and vanishes here, they have to be zero everywhere. Now, the proof is based on the inverse scattering method, and therefore he needs the second solution to be zero. It's not that you take any two solutions, and if they agree in the semi-line, the result is true, but that's not what he proved, okay? Then this technique is based in the inverse scattering. Then if you cannot modify the equation because the equation satisfied by the difference of two solutions is not the original one, then he needs this. Then in the same regard, we have other results. I will not go in detail. For example, for the KdV, if you start with a solution that have very strong decay at infinity, then the solution becomes very regular. In particular, if you have exponential decay in this form that you are in L2 with this weight, the solution will become analytic. And then, of course, you have very strong continuation principle that you cannot be a constant, right, in an interval and so forth. Okay, that was proved by Tarama. And if you have an open question, this result is unknown if you are not in the KdV. If you are for any other power. Okay, what we want to talk is about this kind of unique continuation for the following equation, for the Benjaminon equation that we will define, for the intermediate long way equation that we will define, for the Kamasa-Hall and related model we define also, and the Benjamin-Bona-Mahoney equation. If you are familiar with this equation, you will be disappointed because all are first one-dimensional models, right? Okay, what we will talk, the question can be posed in higher dimension for dispersive no models, but we would like to restrict today to this model. Okay, there are results in higher dimension for Schrödinger, fractional Schrödinger equation, and so forth, but I would like to restrict here. The interesting thing is that even that they are one-dimensional, the Benjaminon or the intermediate long way equation and the Kamasa-Hall are totally completely integrable. That means that you have another way to solve them in more explicit form. Okay, let's go to the Benjaminon equation. The Benjaminon equation looks like the KdV, but instead of having the third derivative here, you have the Hilbert transform and the second derivatives. That means that the dispersion, instead of being modeled by an operator of order 3, is modeled by an operator of order 2, because the Hilbert transform can be thought as an operator of order 0, right? Because the symbol of the Hilbert transform is the sign that is homogeneous of degree 0. Then this is like derivatives of order 0. Then the Benjamin-Ono equation, even that it was deduced much later by Benjamin and Ono as a model of long internal gravity wave, right? It followed the same pattern as the KdV, because after that it was deduced as a model in wave propagation, it was proved to be completely integrable. Right? Okay, then since we are going to study the Benjamin-Ono equation, it can be the well-posedness in the classical Sobolev spaces have been studied by many people. And since we are here connected with Brazil, is one of these is Rafael Iorio, right? And then many other people. The best result that is known is due to Ionesco and Carlos Kenny, that they proved that this global well-posed in L2 and in any Sobolev with any regularity that is positive. But if you use inverse scattering, then recently Kilip, Lawrence, and Bizan proved that you can prove that this is well-posed for S larger than -1/2. Okay? Then this is and this is sharp. This cannot be improved because you have some scaling there. Okay, another thing that you can prove for the Benjamin-Ono equation is the following. Doesn't matter what regularity you ask in the Sobolev scale, you cannot prove local existence using contraction principle. In a work for 93 in collaboration with Carlos Kenny and Luis Vega, we proved that the KdV can be solved by the fixed point. Then what Jean-Claude, Molinet, and Setko proved is that this is not the case for the Benjamin-Ono equation. The dispersive relation is too weak to do that. That you can see that everything that has been proved for the KdV, you try to prove it for the Benjamin-Ono equation. Sometimes you prove that it's true, sometimes prove that it's not true, so forth, but it's the typical things in the dispersive community. Okay, then what is the local unique continuation result that we can prove here? Well, it's the following. Suppose that we have two solutions that have some regularity, right? This is not sharp, but this. You have two solutions that have enough regularity for the Benjamin-Ono equation, and they agree in an open set, they have to be equal everywhere. I mean, this is exactly the result that Schroeder and So have for the KdV equation, right? But he proved that, Jean-Claude proved in 1987, and this was proved 33 years later. And that is a very strange thing, that a question that has been open for 33 years, and you will see that is, okay? This is what we have. The result of Jean-Claude is 87. The result that we got is in the 33 years later. Why? Well, why is, let me explain in some sense why. If you have the KdV, and suppose that the solution is 0 here, and you are in this, and then if this is the solution that you have, you can define a solution to be, you want to be equal to, in this part to be equal to U, and in this part to be equal to 0. And you can define U2 to be the opposite, to be equal to U1 here and to be 0 in this part. That means that if you are 0 here, and you decide to restrict yourself in this strip, and you are 0 here, you have two solutions, the U that is given to you, or you can extend this to be 0, and still you have a solution in this side. You cannot do that in the Benjamin-Ono equation, because the Hilbert transform effect is something not local. It depends on all these values. If you truncate and do anything, you don't have that. Therefore, this simple argument that you use a lot when you are applying Kalderman estimate, that is to apply truncation and all these things, will not work. And they really want to do Kahneman estimate for the Benjaminon equation, and that was the problem. And in fact, right, you can prove the following. This is a stronger result, but this is the same proof. Suppose that we have solutions with enough regularity, and suppose that for some particular time, you have an interval that these two solutions are equal, and the derivatives in t in that interval are equal, then the solutions are equal everywhere. That means your condition now is not in an open set. The condition is only in an interval, E0 and AB. You have reduced all your conditions to this interval. Then, in fact, this is false. This result is false for the KdV. If you have two solutions of the KdV that are equal in this interval, the time is the equation, because it's local, gives you that this also is true, and it's not true that if you have these two, by having this, it's not true that this solution will be equal after that. That means that not only you prove the unit continuation for the Benjaminon equation, you prove something stronger that was known for the KdV. And we will see that this is the kind of argument that you will like to ask. The question for non-local is not about an open set, it's about an interval. What happens if you are in one dimension? Okay. Okay, the proof is very simple. I don't want to. The proof is very simple. You say, suppose it goes like this. Suppose that you have a function u that is 0 here, and the Hilbert transform of this is 0 here. Then this, okay, let me do it with f. It will be better if I do it with f. Okay, the proof is something that you learn when you study Hilbert transform. Suppose that f is 0 in the interval AB. Suppose the Hilbert transform is 0 in the interval AB. Then you take u to be harmonic and u of x0 to be f. Then you know that the b is the harmonic conjugate. And the boundary value of b then to the Hilbert transform of f. Then what you have now is an analytic function f that vanishes here. And it's analytic in the top. Then by Schwarz reflection principle, you will see that f has to be 0 everywhere. You use Schwarz reflection principle, then you have an analytic function that have an accumulation of 0 inside the domain of analyticity, then they have to be 0 everywhere. That's the proof. This was known for everyone that have taken a class in singular integral. Okay, what is interesting, this is the proof. What is interesting is the following. If you have a function, you are proving this. If you have a function that have s derivatives, s larger than 1/2 to make it continuous in the Sobolev spaces that take real values, and suppose that the function and his Hilbert transform, okay, I'm sorry. Okay, I was here. Okay, if you have a function that vanishes and his half derivatives vanishes, that is exactly the half of derivatives is exactly the composition of the It's not half of derivatives. It's the Laplacian to the power 1/2. Suppose that you have a function that is 0 for x in an interval. Then you have to be 0. Okay. This is exactly what we just proved. If you have a function that the fractional derivatives of the fractional power of the Laplacian with power 1/2, that is exactly the derivatives composed with the Hilbert transform, is 0, and the function is also 0 there, then you will have that the function has to be 0. Well, immediately when we saw this, we want to generalize this, but we were late because a few months before, Grosch, Salo, and Gunther Ullmann proved the following. And this is a very interesting result, is the following. If you have a function in Rn that happen to be in a subwhole space, doesn't matter what index, and the function itself and any fractional derivatives between, right, vanishes, this function has to be 0. That means that the fractional derivatives are extremely non-local, right? Because if you have a function that is 0, right, any integer derivatives of this will be 0. What you have is that you cannot be 0, you take something fractional. And this was proved using some argument introduced by Caffarelli and Sylvester to realize the fractional power of the Laplacian as an extension operator of some elliptic boundary value problem. Okay, this is what we proved for the Benjamin-Ono equation. Okay, if we go to the intermediate long way equation, and we will not spend too much time here in the intermediate long way equation because it's kind of different. When the intermediate long way equation has the nonlinearity similar to the Benjamin-Ono and the KdV, but it has this operator, is the one that gives you the dispersive linear part. This operator is coming from this one that is not local, that is composed with the second derivatives. This L sub delta is this parameter that you will see why the delta appear. It has to do with the principal value of this operator with this symbol. It's kind of a singular integral where this is a kernel, and this, why do you want to complicate things so much? Okay, this is the idea. The idea is this equation is integrable, and when delta goes to infinity, you will be close to the KdV, and when delta goes to 0, you will be close to the Benjamin-Ono equation. And you are passing from the Benjamin-Ono equation to the KdV, right, by an integral model. And this is exactly what was proved by Abendallah, Bona, Phelan, and so. They proved that when delta goes to 0, this is all. Okay, this goes to 0. You converge to the KdV. When delta goes to infinity, you convert to the Benjamin-Ono equation. Okay. Then the result that we prove for the KdV also apply in this case. If you have two solutions of the intermediate long way equation that agree in an open interval, and the derivatives in time is also equal in that interval, then they have to be equal. Okay? The same result that we prove for the Benjamin-Ono equation hold for the intermediate long way equation. Of course, it's more complicated. The extension of analyticity will depend on this delta, because when delta is infinity, you have what we say for the KdV. When delta is 0, this is not true, because the result, as stated for the interval, is not true for the KdV. Okay, let's go to the next model that we are going to study. Is called the Kamasa-Hall equation. Okay, this equation was again was interesting because it was deduced by Fuchsenmeier and Focus as an example of equations that have many symmetries. Okay. Later, Kamasa and Hall derived this equation physically as a model for shallow water wave, right? And later it was proved to be completely integrable. I mean, this is the pattern that you have. Okay, there are many interesting things, and there's a question. One, maybe one of the most interesting one is that have solutions of this form, that they are called picons. There are solutions that a form of traveling wave that they are not smooth. They are only Lipschitz. In fact, these solutions, when you see that the speed that is c depend of the amplitude, then if you put different picons separated, they will interact in an elastic way as the soliton, because this model is completely integrable, right? Okay, then you can rewrite this equation in this form that is non-local. Okay, you rewrite this equation exactly in this form that is a non-local form. And this is what is very practical to write this, because it doesn't involve any higher order derivatives of order 3 or anything like this. And then you can prove that the Kamasa-Hall equation is strongly well posed with S larger than 3/2. And you have continuous dependent, unique, persistent, and everything that you want, except that the picons are exactly the example that you have of functions that are not in 3/2. This is a typical example of this function is not. Then you have a local existence that is missing all the interesting solutions. But suppose that you say, well, but I would like to include the picons. Suppose that you try to work in subole spaces, or instead of being in L2, in LP, then this is a still false. This is only Lipschitz, it's only truth in here. This is only Lipschitz, it doesn't have any integrability. You cannot put P less than infinity. Then the best that you can do is some result that we did with Linares and Sideris is that you can prove that you have an existence, but you cannot prove continuity in the Lipschitz norm because the translation is not a continuous operator in the Lipschitz norm. Translation is not a continuous operator. Then you cannot prove this, but this is this local existence include, because you put H1 and Lipschitz, include the picon solutions, and then you can prove that you have some persisting in H1 boundedness in the Lipschitz norm, and you have some continuous dependent only in the H1 norm. Okay? Okay, there is, in the periodic version, this was proved by the Lelis, Capellera, and Topalov. There are many other local existence results because this equation have solution that produce singularities, even that the H1 norm stay bounded. That means that this wave breaking type of singularity. Okay, then this, I mentioned some of this. Okay, then what is the unique continuation in this case? The unique continuation is this one, and this is something that we proved with Felipe Linares at IMPA in the year 2020, is the following. Suppose that you have a solution of the initial value problem for the Kamasa-Hall given by the well-posedness in S larger than 3/2 or by the result that we just mentioned. Is that vanishes in an open set, it has to be identically 0. And this is the first example that we don't know if the result is true. The result is true, you put two solutions. the second solution has to be the solution 0. If you put two arbitrary solutions that agree in an open set, we don't know if this result holds. Okay? Then we have to restrict to have unique continuation that the second solution is 0. Okay? This result extends to the periodic boundary value problem, and in the periodic value of the problem, there are some previous results by Brandolez and Cortez, and Brandolez itself, that they are different because they assume that the solution exists globally in time. Okay. Okay. Then, if you observe the proof that we have with Felipe, then you can see that you can make it a little bit stronger. You can say, suppose I have a solution and the solution vanishes in an open interval. This is T0, this is A, and this is B. Suppose the solution vanishes in this interval. Moreover, the derivatives in time along this interval of the solution is not strictly decreasing. Then you have to be 0. Again, the condition is in an interval, it's not in an open set. This is stronger than that. But it has the disadvantage that you are plugging here 0. You don't know if this is in general true for any other, for an arbitrary, this U is any other solution. Okay? Okay, then you can say, well, at least is 0 an important value? Well, with Felipe, we just proved, in fact, it's not written as a paper, but we just finished the proof that say the following. There exists, if you choose any constant that is not 0, there exists data that satisfy that they are equal to the constant, and the derivatives along this interval is 0, and the solution is not equal to this constant. That means that the constant to be 0 is crucial. You can be equal to any constant that you wish and have the property that this is not decreasing and not be equal to the constant. Because this initial data is compact support, then you will not be able to say that you are identically equal to this. That means that the constant 0 is the only one that is there. Okay, then the same result holds for all this family of solutions. This family is, if you put B equal to 2, you have the Kamasa hole. If you put B equal to 3, you have something called the Gasperi-Prossetti that also is completely integrable and have Picon solutions, right? And they are complete. You will see that in these two cases, the interaction of the Picon is elastic because they have soliton. If B is between 0 and different than 2 and 3, then the interaction is not elastic. You have the traveling wave notice. Okay, finally, the last 5 minutes, I would like to consider this equation that is called the Benjamin-Bona-Mahoney equation. The equation is very similar to the KDV, except that instead of having 3 derivatives in X, one of the derivatives in X is changed by derivatives in time. Then you can rewrite this equation in this form. And this equation was deduced or was proposed as a regularized version of the KDV equation and have appeared in other applications. And this is what we want to study. And you can write this equation. Now you have that the dispersion is modeled by this operator. Okay. You can rewrite this way. This is the linear part. This is the dispersive relation that is strange because it's homogeneous of degree -1, 4, but this is, you can write it this way. And if you write it in this form, then you have that Bond and Setko prove that the initial value problem for this equation is globally well posed in L2, in any subordinate spaces if you wish. You can extend this to the in LP setting, but more than that, you can extend this even for any holder space of this form. Then the initial value problem is well posed in any of these spaces. Okay, that's something that we prove. And what is the unique continuation in this case? The unique continuation is this. Suppose that you have a solution of the initial value problem associated to the BBN equation, right? That is in this space where the initial value problem is well posed. Suppose that you have one time and one interval that you equal to -1, and you have that derivatives at the end of the interval is larger in time, is larger than at the beginning. That means that the derivatives is not decreasing. Then you have to be equal to -1 everywhere. Okay, then that means that if you want solution in the HS, you cannot have this condition because a constant are not in the subordinate spaces, right? If you accept the homogeneous one. Okay, then you're going to complain, well, that why -1? Well, let me tell you that if you go to an example, modify an example that Rosier and Sand prove, you can have this solution that is a stationary solution that is equal to 0 in the interval, it's equal to -2 in this interval, and it's equal to 0 outside this interval. This solution belongs here, right? And satisfy all the conditions that you want. Then -2 is okay, but -1 is not. -1 is the only value for what this holds. In fact, this is what we prove. You can have, if you give me a constant that is different than -1, I can find an interval AB and a function that have compact support that take the value exactly equal to this constant in the interval, and the solution of the initial value problem for the Benjamin-Borna-Mahoney equation vanishes in that interval, the derivatives in T, and is not equal to this is 0. Okay, then since this has to, I think, do I have to finish at 40?
Sorry, Professor, you have time, like 10 minutes.
10 minutes?
Yeah.
Okay. Okay. Okay, then we prove that for the BBN equation, the critical value was -1, and everything that you want to prove is not true, that you are not -1. Then suppose that we consider the periodic boundary value problem of this, and then let's see what was previously known in this regard. Rosier and Sand prove the following unique continuation when you have a solution of the periodic boundary value problem. Suppose that you are in H1. You need this regularity. You have to be continuous. More than continuous, you have to be H1. Suppose that you are positive. Suppose that you are not too big. And suppose that you vanishes in an open set, then you are 0. It's a different class of unique continuation, but what we prove doesn't imply this one. This one doesn't imply what we say. Then this is a classical unique continuation, but you need all these conditions because in some sense you are saying that this cannot move too fast if you put all the restrictions. Then what can we prove? This is a joint work with Christian Hong, a PhD student. We prove, suppose that we are in the periodic boundary value problem for the right setting, and suppose that you are equal to -1 in an interval, and the derivative with respect to time in that interval is not totally decreasing, then you will have to be equal to -1 in the full domain, right? Depending on the regularity that you have at the beginning, almost everywhere, if S is less than 1/2, everywhere you are less. And also, in the same setting, in the periodic setting, if you are not equal to -1, then you can find initial data, right? Such that they are in the interval AB, they satisfy that they are equal to this constant, and they satisfy that this is not decreasing. But since, right, you are not going to be equal to C0 all the time. Right? There is a. Then the solution in this case will not be equal to the constant all the time. They mean that the constant -1 is the only one that gives you what you want. Okay. Okay, then in fact, you can cook an example. If you modify Rosier and Chand example, you can cook that the explicit solution that do exactly what you want in the periodic setting. If you are not equal to -1, then you take this function take the value, this f, if you are not -1, this value is taken twice, then you define your function to be in the interval equal to this, outside the interval equal to this, and then you have a solution that is a stationary solution of the BBN equation. And this is the idea of Rosier and Chand. Then that means that -1 is the value that is. Okay, I have something else to say, but I will prefer to stop here.
Okay, Professor, thank you, Gustavo, for this nice talk. Let me open for questions or comments. Juan, can you open the audio, please? Las personas de la audiencia pueden poner las preguntas en chat. Okay, everyone can write in the chat and the questions.
Okay, let's see if I can.
Okay, but it's open the audio and the video. Okay, let's open for question. Maybe I can start. Just a curiosity, Gustavo, because, well, okay, I work in some kind of dispersive problem, but in control theory, and in general, I decide to work in the bounded intervals. For example, KDV in the bounded intervals. My question is, we can use, for example, the same machines or the same tools to prove the unique continuations, not in the sense of like Rosier and Zhang, but in the sense of your
Yeah, for the Benjamin, no, in the periodic case, yes.
But in the bounded interval, imagine that I have a 0L, 0T, for example. What's happened in this case, for example?
Okay, in the interval.
Yes.
Okay. Well, okay, let's see. In the Benjamin, no, you need some property of the Hilbert transform that can relate with analyticity. That is okay in the periodic case, but I don't know if you put with boundary condition, are you going to put that you can relate that the Hilbert transform is a boundary value of the Laplacian, right? Right. You have to be sure that have to work. And but that is only in the Benjamin equation. Then for the Kamasa whole equation, for example, then the trick is different, right? I think that you can adapt the trick to the interval.
A for KDV as well, probably.
Well, for the KDV, then it's then it's not local. Then it's a different story, because then you return again to have that you need to have these two solutions to be equal in a open set. What we are trying to do here is for non-local model, you don't need the open set, you only need an interval.
Right, okay, understand. Okay, nice. Okay, more questions or comments? And let me check in the chat. Where's the chat here? Okay. No questions, no comments? If not, let's say thank you again for Professor Gustavo. Thank you,
for the
Professor.
invitation and for the
Bye.
patience.
Really good talk.